Hi, I'm Aaron Goldman, and this is Papers We Love Too, the SF chapter of the Papers We Love paper reading group. Today we're going to be going over the paper Laurel's Low-Rank Adaptation of Large Language Models. After that, we will take some time for questions, and then I will stop the recording and we'll have a off-the-record discussion. My name is Aaron Goldman. I've been working on AI systems and distributed systems for years, starting my time at Georgia Tech and Georgia Institute of Technology using AI for spam filters and malware identification pipelines. Went to Google, where I was on the trust and safety team, detecting people who were doing fake activity on YouTube, purchase likes, things like that. Spent 4 years doing trust and safety at Twitter, as well as worked at a handful of startups. T-Cell doing firewall things, again, use AI to detect anomalous behavior, and Blue Sky working on social networks where the AI was the ranking algorithm. The paper we're talking about today is low rank adaptation of large language models. It's a paper that came out of Microsoft that had this problem that they were trying to run ChatGPT, and there's a bunch of different topics and expertise and modes that you would like to run the GPT model on, but it was very expensive to switch because every time you fine-tuned the model to become expert in another task, you had another 250 gigabyte model that needed to be in memory. So if you wanted to switch between one or the other, you had to wait to pull 250 gigabytes out of disk and stuff it into your GPU memory and then start that task. So the real problem that they were trying to solve was how do we quickly adapt a model that is in memory so that it's fine-tuned without having to have several dozen large models laying around and pay all of this operational cost to do the switching. The second benefit that they were looking for a lot was how can we try to reduce the costs of training? So to fine tune a model, you've got hundreds of billions of parameters that you're trying to fine tune. And every time you get an example, you now have to figure out what is the appropriate update for those hundreds of millions of parameters. So they felt that they could solve both of these problems by trying to shrink down the thing that they were trying to do to a low rank adaptation, which is where this name comes from of low rank adaptations. The most important diagram, I think, in this paper is the very first one where they describe their model. They simply describe it as we have these pre-trained rates. There is some foundational model that we've trained on all of the texts that they could find on the internet and all of the books that they could find and things like Wikipedia and private databases and just try to get your hands on every last scrap of text that you can get your hands on and train on that so that you have a model that just represents how does humanity use words. After you have this big model that's been trained on everything, then they say, okay, let's freeze that and say this is going to be the foundation model. You'll hear that term a lot in AI these days, a foundation model, because it is the thing upon which we are going to build other stuff. It was expensive, but once we have it right, it's now relatively cheap to make copies and distribute it. It's just a 200 gigabyte file. That's somewhat large, but these days we're actually pretty good at dealing with 200 gigabyte file. And then on the flip side, they're going to say, okay, let's squish down to this low rank representation that is much, much smaller and do the fine tuning on that. And then we can simply add that to our model to change the behavior. So the fundamental idea that's going on in these large language models is that matrices can turn inputs to outputs. It feels like a very dumb thing to be pointing out that we can implement functions, but essentially that's what we're trying to do. The goal of all machine learning is can I learn the function from some input to some output that gives me the behavior that I want? And fundamentally, at its most abstract level, it's just an n by m matrix. If I take my input data, whether that's a string of text or an image where I've just linearized it by putting all of the columns in one big row, or labeled ranking data or weather simulation data, no matter what kind of data we have, we can represent that data as just a sequence of bytes that is going to be our input vector. And no matter what the output we're looking for, whether that's a tag or a label or an image, you can be going image to text, text to image, text to text, image to image. It's all just the output sequence is a series of bytes. And there is some matrix that can be learned that will turn the inputs into the outputs that you want. So we're going to take a whole bunch of examples of input and a whole bunch of examples of output and come up with a model that is sort of the average of transforming inputs to outputs. And if we get that right, we can not only learn to give the examples that we learned on, but hopefully generalize to something that is more useful. The problem is that this model is potentially too big or potentially too small. If I have a million tokens of input and a million tokens of output, this would be a million by million matrix. That's totally untenable. We need to find ways to shrink things down. So we're actually going to represent our n by m square by two matrices that are being multiplied by each other that are each a rectangular matrix. One that is the size of our input data and times whatever our hidden rank is. And then the output is going to be the size of the output times whatever the hidden rank is. So now I can choose a low rank here and get a much smaller matrix than the square matrix would have been. Or I could even pick a larger matrix than the square. Maybe I'm trying to learn a mapping between two types of data, and they're both represented as 16-bit integers. I'm looking at the amount of power that is being generated by a power plant in 5-minute windows, and I want to know what is the amount of power that's going to be generated in the next 5-minute window. Well, that's actually going to be really tiny numbers. Like maybe it's only 16 levels of measurement or 256 levels of measurement. I may actually want to have a hidden rank that is larger than my input or output data in order to enable me to learn a more complicated model than would inherently be represented. But the point is just that we have now broken this link. We've said the fundamental rank of the mapping that is our function, the level of complexity in our function, is going to be measured by this hidden rank, not by the size of the input or the size of the output. We now have a variable to play with for the complexity of the function. Now, whenever I need to draw this picture, we're going to draw it not as two rectangular matrices being multiplied by each other, but using this shape to say, okay, we've got some input, we're going to a hidden representation, and then we're decoding from the output to be in this output representation. This has two advantages as a way to think about it. The first is I think it's just a little more intuitive to look at this thing and say, yes, we are transforming from input to our internal representation and output. And it makes it a little bit more obvious when you think about what it means to have a multimodal design, where my input encoder, I may have trained on text that was text to text, and my image encoder, I may have trained on image to image. But I can now make that an even richer encoding by saying, okay, now I'm going to take the encoder I trained on text and the decoder that I trained on images and connect them to each other with the same hidden rank. And now start training on pairs of text to image. So now I can start building up all these modes by having several different encoders and decoders that all map from the same hidden rank in the middle. Okay, so what is a LoRA? A low rank adaptation says I'm going to take my previous model that is some big model like ChatGPT that's got hundreds of millions of parameters in it, and I'm going to create a second layer that is going to compress to a much smaller rank, which is why we call it low rank adaptation. That is typically going to be something like 10 to 50 million parameters. So now I've got my big model that's hundreds of gigabytes to load into memory, and I've got a low rank adaptation that's maybe 10 megabytes or 20 megabytes or 50 megabytes. It takes a lot less memory bandwidth to load one of these laurels into your GPU, and you don't actually have to run it side by side. So one way that you could imagine running this is I run all my math through the previous model, I run all my math through the Laurel, then I add the two results together, and that's my output. But actually, I can just add the matrices. If I multiply out the encoder and decoder, I can yet again build something at the scale of the large model. So if I'm a little bit careful about how I do the math and how I handle the rounding, I can actually have a Laurel where I load 10 megabytes of data into my GPU. I do some math to figure out how to update all of the weights in the previously existing model. And then when I want to unload that Laurel, I just recalculate this number, subtract everything out. So now by using addition and subtraction, I can insert a Laurel into the big model or remove a Laurel from the big model without needing to have to reload that whole model again from scratch. So it's really useful to be able to go both ways. That enables me to do switching, where if I keep switching tasks, oh, I was doing image processing, now I'm doing language processing, now I'm doing answering questions in a chatbot, now I'm doing analyzing some particular piece of JSON data. I can keep switching which task I have loaded once I realize which task I need without needing to do nearly so much memory bandwidth. So now we come back to this picture that is the picture we started with and say, all right, I've got my pre-trained weights, I've got these things, and I'm only going to change this one piece that, again, is these low rank matrices. And again, because it's a much smaller number of parameters, we get a secondary benefit, which is there's just a lot fewer parameters here. So every time I do the training, I have to do backpropagation. I have some example input, I have some example output. I take the input, calculate all the way to the end, and say, what is the output that this would give me? Oh, the output I generate does not match the output that I was expecting. So now I'm going to backpropagate and say, okay, how much did these miss by? Fix the first layer, fix the second layer, fix the third layer, and gradually propagate backwards, changing all the models until now it does give me the output that I want for my input. Because there's so many fewer parameters, we can now train this thing with way less GPU time and way less GPU usage and just doing a lot less math. Also, we can do that using a lot less training data because, again, the amount of training data you need is somewhat proportional to the amount of parameters that you want to tune. If you have a megabyte worth of parameters, 10 megabytes worth of data may be enough to train it. If you have 300 megabytes worth of data, now maybe you need gigs of training example in order to be able to change it. So what happens when they actually try this thing? In this paper, they're comparing several different ways that you could fine tune a model. So the first one is this blue dot that they're calling fine tuning, where you say, okay, let's actually take all of the examples from this training example, be that Wiki SQL. Let's generate SQL queries that can search Wikipedia data. Or this multi-language matching problem. We have two different problems that they're fine tuning on and trying a bunch of these different methods. So the first method is fine tune, just train until you understand the problem and see how well you can do. So here we see the number of parameters that you have to train for this for the fine tune the whole thing is all of them. You need a lot of data. You need a lot of compute. This is very expensive. This is the thing they're trying to get away from. And we see that, keep in mind, this is a log scale. So this is 3 orders of magnitude more data than anything that they tried with the Laurels. So the biggest Laurel that they tried was 1,000th of the size of the full model. And the smallest Laurels that they're trying are much smaller than that. They're 10,000th or 100,000th the size. The second thing they compared it to is prefix embed. So with prefix embed, you say, we want to train our large model to understand this particular task. So we're going to put some flag at the beginning of the thing that we are training on that says we are on this particular task. So rather than the input being, here's the input data, the input is, here is a task identifier that tells the model what task I'm working on. And then here's the rest of the input data. And what we see is that as we put more and more parameters into this fine-tune training with prefix embed, we do better and better and better as we specialize on the task. But eventually we start consuming so much expertise in knowing which task we're on that we start losing accuracy again. So we can't just scale that up completely because then you end up feeding all of your parameter space to this fine tuning parameter. And I think this somewhat is reflective of the argument of can't we just fix this with prompt engineering? Maybe the reason that I'm getting not well drawn faces, maybe the reason I'm getting bad answers from my language model is I just didn't ask the question the right way. Maybe as if I frame it and I start with my thing and I'm like, I just need to tell it that you are someone who doesn't like to lie and you're someone who likes to do math very precisely. Maybe it won't make all these math mistakes. I personally think, although the paper doesn't really make this point, doesn't argue this point very strongly, that the same things that make it hard to just tell it what task you're on suggest that as we put more and more complexity into our prompts, we'll eventually saturate that and get to the point where it just keeps getting worse. And eventually, we do really want to teach our models how to perform specific tasks. We don't just want to describe that task very aggressively. The second thing they tried is prefix layer. So let's actually put an entire matrix multiply before we start doing our processing that says transform the input into an input that will get the model to do the right thing. That gives us a bunch of parameters to tune and does better. Excuse me. Here, right off the bat, we're doing much better and can get to much larger models training parameter sizes because we're not choking out the thing that is doing the rest of the work by consuming all the parameters. We're adding new parameters where we can put this stuff. And the last one is having a full-on adapter that says we are going to run a thing before and after and really just try and fix it and leverage the model as a tool. This adds a bunch of latency because you're essentially doing 3 rounds of processing. But this does get to the point where you can really fine tune and get to good results, even if you have to use a lot more parameters to get to the same results as they do with the Laurel. And what we see with the Laurel is it very quickly, with very few parameters, jumps up to the point where we're getting very high accuracy. So we get from 84 when we're not tuning this thing all the way up to 92% accuracies or 75% accuracies, depending on the benchmark. And we do as well. In the wiki sequel, using just 10, 15 million parameters, we are already doing as well as if we had fine-tuned the entire model. And interestingly, with the multi-NLI matched, it's actually doing better than if you train all the parameters. And your first instinct is look at that and go, that's not possible. How can changing some of the parameters do better than changing all of the parameters? Surely, if I can change all the parameters, I can do the optimal thing that I would want to change. And the theory behind that is you didn't have enough data. When we're doing the fine tuning, you have to put a bunch of data through and you have to tune a large number of parameters. And it's true that if you had enough examples of your task, fine tuning all of the parameters would be the best that you could do. But if you have a finite number of examples of your task, the fact that it is so many parameters, it can kind of memorize the training data in a way that it can't with the Laurel. So you end up overfitting to the specific training examples you get and doing worse on the benchmark. Okay, so I need to take a detour now away from the paper because the paper just sort of assumes that you know what singular value decomposition is. I am not assuming that the audience of this video necessarily knows what singular value decomposition is. So the idea here is you can take any matrix A and represent it as the product of 3 matrices. We can have a U matrix that says I am going to convert all of the stuff that I have in this matrix to a better basis to represent the ideas that are in the matrix. I then have a diagonal matrix that's just a bunch of weights that scales things up and down. And then I have my V transpose matrix that translates everything back. So the idea is turn your data, scale your data, and then turn the data back. And now I can approximate it. But the goal with a singular value decomposition is we're not just turning the data, but we're deliberately turning the data so that the most important vectors show up first. So, for example, if I give you this data, which is on a 2D plane, or we can imagine that there's a third dimension, but we're just not seeing them come out for you. There's clearly a lot more variance along the oval than there is across it. So if I'm trying to represent this data with this is my y-axis and this is my x-axis, then it's going to be somewhat hard to represent the data. But if I turn it and say, okay, I'm going to take the principal component, the thing that is the place where there is the most variance in that dimension, and I'm going to line up all my data to that and say, okay, that's my x. And then the dimension that's got the second most variance is my y. And the third most variance is my z. And I just go down the list until I have gone through my matrix. So in a typical one of these pre-trained weights, you have something like a 300 dimensional space, or in some of the larger models, a 1200 dimensional space. So here we say, I'm going to go through and I'm going to realign my data so that it's 1200 dimensional, but that the first one is the one with the most information, and the second one is the one with the second most information. So as I go down my U's, this is the most important, and that's the most important, and that's the highest weight. And as I go down, it becomes less and less important to the output. And these weights get lower and lower and lower as it cancels things. And then as these go across, it gets lower and lower. So we're really trying to push all of the energy into this sort of top corner of the representation. And that's going to enable us to do something special, which is truncate the thing. So I can keep adding S's until I am perfectly recreating my A. Or I can say, you know what? I'm just going to take the top n rows and the top n columns and the top n diagonals, and I'm going to set everything else to 0. And now I don't have to store it. And I've thrown away a bunch of information, but the information that I've thrown away is the information that wasn't helping me anyway. So that I get something that is much closer to the fundamental rank of the representation that I have learned than the arbitrary rank that this A matrix was going to be. So here's an example from a much older paper called Eigenfaces. And the idea behind Eigenfaces was, can you represent an image of a face by a linear combination of other images of faces? So they got several thousand pictures of faces and they lined them all up and they calculated, okay, what is the principal component of a face? The most important thing that makes a face facey is that it's got eyes and a nose and a mouth. And now I can take just 25 floating point numbers to represent this face. And if I represent this image that was 256 by 256 pixels, so that's what, like 4,000 numbers representing this face. And instead I use only 25 numbers, I can now get a face that like looks like a face. Most of faciness as a concept has been captured by this decomposition into these matrices and just storing these weights along the diagonal. With 50, it doesn't just look like a face, it's clearly a masculine face. By 800, it's not just a face, it's clearly that guy specifically. And with 1600 floats, now we're getting to the point where this is still much less than representing the entire 256 by 256 by 3 image, but you almost can't see any loss. My guess is that the YouTube compression has taken more out of this face than the ability to tell the difference between the original and the compressed face. But we can also represent concepts that weren't in the original training data in this way. So here is an attempt to describe a dog using linear combinations of the means of faces. And what we see is with, only 25 means of faces, it still basically looks like a face. By 100, it's a messed up face. By 400 or 800, it's very dog-like. And by 1600, oh, it's not just a dog, but like it's clearly that dog. You can recognize whose dog this is a image of with these 1600 representations. But there is some question of is the information you're trying to represent close to the concepts that are already in your representation? So if we try it again with a teacup, we find that, well, you could represent a dog pretty well using faces. It's actually much harder to represent a teacup. We get to the end of this teacup and it's still got a lot of fuzziness and just not clarity. You can sort of see the teacup in the image. You can't really see the spoon or the curtains at the top because that's just a concept that didn't represent very well in the space that you're making combinations of. So you don't want to necessarily just use a bunch of laurels to represent things. There really is a value to having that base image have understood a lot of concepts. So you still want to train the base on as much text as you can get, as many concepts as you can get, as many places as you can get. And then you're going to be able to use the laurels to represent linear combinations of all of those concepts. If this had been trained not on faces, but on huge numbers of highly generic images, it would have been forced to learn much more generic concepts like edge detection and light and shadow and things that would enable it to represent this teacup much better. Okay, so how big should a laurel be? The paper talks a lot about trying to decide what the optimal size is for one of these laurels. And the answer largely comes from this singular value decomposition of the space. So we take the big matrix and we divide it up and we say, okay, in a place that's fairly early on, well, there's still a lot of power in the principal component, we see a lot of aspects of the concept that was learned. So in the eigenfaces example, this spot still looks a lot like a face. The thing that we are learning in this particular level of the principal components, the early dimensions, really looks like a concept that is a human concept that you would find in the text that you trained on. At this level two, where we start to get to like 1,000 dimensions, now you can sort of see faceness, like there's a bit of density where each of the eyes are, and there's clearly a nose and there's clearly a mouth. By the time we get to the point where we're way down the list of power, now it just looks like white noise. So the trick with these decompositions is you essentially look for the entropy drop. When you are in the early dimensions, there's not going to be a lot of entropy there. When you go to the high dimensions, it's essentially going to look like white noise. Once you get to the point where your additional dimensions of representation are only representing Gaussian white noise, you've hit a point of diminishing returns. So when we think about the case where we had these dots and we weren't able to fine tune very well on these examples, well, to some extent, what we've learned at this dot is both the concept that we're trying to learn that makes us good at a particular task, and we've memorized a bunch of white noise. Memorizing the white noise didn't really help us. So if we can drop back to a Laurel size that says, here is the amount that we really want to represent deltas on our matrix that are not just white noise over our matrix, we're actually going to learn better. So it gives us a way to tune, but not overfit our data simply by doing a low enough rank adaptation that we don't end up overfitting the data. So that's our basic pattern. The fewer and smaller and tighter our Laurel is, the more we're forcing it to generalize. And the bigger and longer and more parameters there are, the more we give it the ability to memorize. So depending on what the task is that you are trying to do, you might want to do something very different. So for example, it might make a lot of sense to train a fairly large rank laurel for subject matter expertise. I'm ingesting every law case that has ever been written because I'm trying to understand the concept of law. Maybe I want a really big laurel for that because I'm actually trying to memorize a bunch of information about the way the law works. For the task of, I would like to have my output come out as a valid JSON object, I probably want to use a much smaller, tighter Laurel because there's not that much information in how JSON is formatted. You really want to force it to try to generalize rules and not try and memorize a bunch of stuff like, oh, quotes are much more likely to come after periods because the sentences tend to end with periods and that when the quote comes. Like, you don't want to give it enough space for it to memorize things that are essentially noise in your training data. So now we're back to this image that I think is a very key image for understanding this paper, which is by using laurels, we can get to the point where we very quickly have memorized a lot of the information that will really help us do the task. And if you have a benchmark that's good at telling you when you've memorized enough information to be useful, and as we continue memorizing more information and making larger and larger laurels past that point where we've basically got the task, you're just memorizing a bunch of noise. And while you will get better at spitting out the training data, you will not necessarily get much better at the task that you're trying to train. So now they want to test it and say, okay, how do we know that the laurels have actually learned something interesting? We're going to go through and build a whole bunch of subspace similarity comparisons. So here we have, I've trained on two different cases of two different seeds. We initialize the laurel with totally random state. We initialize a second laurel with totally random state. We train on the same set of training data. And then we say, okay, how similar are these matrices that we have built when we multiply them out? And our hope is that because the shape of our matrix is these two matrices multiplied together, that what we're going to get is that the combined matrix has most of its energy in the sort of first column and first row. And what we see is that that's exactly the pattern we get. If we compare two random Gaussian matrices, there's no correlation. The information's just wherever the information is. But if we compare two multiplied out matrices that have been trained with laurels, we find that the changes end up in the early columns. And despite the fact that we started with two totally different random seeds, we have in fact been pushing a lot of what we've learned up and to the left so that we can simply store these two rectangular matrices and zero out all the stuff at the bottom and not actually lose that much of what we would have learned. So we, in some sense, are restricting where we're learning the information because we're pushing stuff up and to the left. But also, we're giving it a lot more flexibility than if we had simply said, oh, we're going to do the training and we're just going to freeze the entire bottom. You know, one way that you might imagine making it cheaper to train these models is to just say, oh, we're going to take the first n rows and the first n columns of the matrix, and we're going to let you train on those, and we're just going to not back propagate through the rest of it. But that would actually really hurt your accuracy because suddenly you're having to fight against a bunch of parameters that you can't touch. Whereas here we say, yeah, focus your energy near the top, but if there's something you need to fix that's lower down, you can put exponentially less of your energy into fixing the stuff that's exponentially lower down. So you can actually fix it and you get much more efficiency than if you just trained a small set. The second thing that you get as value is because the decomposition is going to come out differently for different tasks that you're learning. If I had just said, you get to train on the top column and you get to train on the left column, and then I trained two different expertise. So I say, okay, you become a good accountant and you train a Laurel on being a good lawyer. And now I want to ask a question of base knowledge plus accounting knowledge plus law knowledge. Adding two laurels to my matrix wouldn't have worked well if I just said train the top, train the left, because they would clash with each other. But because I'm doing the transformation the way I am, each one is going to focus its energy on correcting the places in the matrix that it needs to get its expertise. So you can totally have a giant model and then two different laurels that are each a thousandth the size of the big model and load them both simultaneously. The paper doesn't talk about this in the context of images, but this is one of the places where we've really seen this shine. They imagine it as load the law module and load the accounting module, and now you have an expert in both law and accounting. What I've seen more often is load this module that convinces people to be wearing medieval clothes, and load this module that convinces the image generator to make things look like anime. And now I have anime characters in medieval clothes, and I can take a bunch of different modifiers or classes of images and train different attributes that I want to have and then combine them. So, okay, this one I'm going to train on all the Van Gogh paintings. That one I'm going to train on athletic sports stuff. And now I have screenshots from athletic movies as painted by Van Gogh. Like, it's really interesting to be able to train all these small expertises and then add them in together and get interesting combinations of them. And part of that is enabled because this low rank adaptation sprays its changes to the places that are most effective to make changes in the large matrix, rather than simply saying, I'm going to give you a million parameters that you're allowed to touch out of the hundreds of billions of parameters that you're allowed to touch, and hope that that's enough to get the fine tuning that I want. So now we've basically accomplished what the paper set out to accomplish. We have this giant thing with pre-trained weights. We have a small rank adaptation where we have these two matrices that have an upper and lower multiplied together to get the same shape as the pre-trained weights. And we can join them together and add them. So for training, we're going to keep it separate and leave the pre-trained weights entirely frozen. Go through both paths forward, but only back propagate through one of them. So if we forward propagate through both paths, we back propagate only through the path that is a 10,000th the size. We program a 10,000th of the parameters, and we need a 10,000th of the amount of information to fine tune as we would if we wanted to train the entire system. And we get a thing that we can add these laurels in without causing a bunch of degradation later. So it leaves us with this imagination of what the future is going to look like, where we have some foundation model that's going to be very big. In the time when this paper came out, most of the foundation models were 200 gigabytes. If you go to a foundation model from, say, Facebook now, it's 400. DeepSeek was 500 gigabytes. So we can expect that these foundation models are going to keep growing and getting bigger and are going to become very expensive to train and even very expensive to just fine tune. So we can expect to then have a layer of big laurels that are subject matter experts. Oh, I want to train maybe a 64 gigabyte laurel that's much smaller, not on petabytes of information, but maybe on a couple of terabytes of here's every law case that has ever happened. And then you're going to have a much, much smaller task specific decoder that says, okay, now I have specific examples of this kind of legal question is being asked and answered, or this particular kind of brief is being written, or all the specific tasks that you want, that you have a lot less training data. And then finally is user personalization. As we use these services and you keep asking questions and getting answers and doing things like clicking the thumbs up button next to some answers and the thumbs down button next to other answers, you probably want to train your models to give answers that you personally like. But you don't want to spend a huge amount of resources doing that. And there's just only so many questions that you asked and you answered. The amount of text that comes specifically through your having personally ranked it is orders of magnitudes less than a task specific, lots of people doing this task, which is orders of magnitude less than all of the text that has to do with your segment, which is orders of magnitude less than all of the text on the internet. So those are going to end up being very small user personalizations, but can still be very useful because there are people who just have voices that you like. the person who listens to a lot of NPR and would like their bot to respond to them in clear, highly factually, emotionally calm answers is going to be very different from the one who wants the thing to sound like their best friend and give very conversational, casual answers about everything and not be very formal or rigorous in the ways that it's answering questions. So to me, this is the way I see the future of training and why this is a paper I love. Is it leaves me with this inspirational moment of we're going to have these foundational models that cost a huge amount to train, but we need very few of them. Like maybe two companies make a foundation model once every 10 years, and there's an open source model that's sort of continuously being trained up and getting a little bit better as large numbers of community people contribute a little bit of processing to improving it. We're going to need hundreds of subject matter experts on the order of the number of college majors that there are. There's going to be that many subject matter experts that you really want to fine tune the laurel on that particular skill set. Task specific, there's going to be orders of magnitude more tasks, but they also have orders of magnitude less data. So the task specific experience is much cheaper. When it comes to policy, how do you want the system to behave? It's again more. And then individual personalization, well, that's billions. Everybody's going to want to be doing some individual personalization of their tasks based on their own feedback so that the AI can act in the way that you personally enjoy interacting with the AI. But that's also by far the cheapest to train. So we actually get this nice level that, well, it's true, it's super expensive to do foundational models. They amortize very well. And while it's super cheap to do personal, everyone does it. We're going to end up as humanity probably spending about the same amount of energy training each of these levels in total. Because this is a billion times cheaper, but you have to do it a billion times. And this is a billion times more expensive, but you only have to do it a few times. And that's my conclusion. That's what I got out of this paper and Laurel's. And I think we really do have a future that is going to involve a lot of tasks and a lot of fine tuning and really coming to understand these. I am particularly interested in this policy layer because I've spent a lot of my life doing trust and safety on AI systems. And I think it's really powerful to put your policy layer right here and say, I'm going to bring all this stuff down and then I'm going to redo the weights and then I'm going to put things back up so that when you do lots of different things, hey, maybe I'm encoding text and generating an image or encoding an image and generating text. Well, I don't want my thing to do pornographic stuff or describe violent behavior. All of that can be put in a policy layer that just goes from hidden rank to hidden rank. And now I don't have to have a separate trained thing to say, don't be obscene in pictures, and don't be obscene in text, and don't be obscene in labels, and don't be obscene in decoder that one of my customers made up and trained for themselves for their own particular data. You can just say, hey, I'm going to train everything with this layer in the middle that I can say, oh, here's my don't be obscene Laurel. And it doesn't actually care what your task is. It's doing this transformation in a way that just convinces it, don't be obscene at the conceptual level of being obscene. So we can start having don't be obscene be like this kind of face rather than trying to represent obscenity like it's some teacup that is very hard to actually convince your system to not do because it just wasn't ever trained to understand those concepts. I will end. Normally, I end these talks by asking people to come work with me on whatever I'm working on. But at the moment, I am looking for a thing to work on. So I'm going to do my reverse recruiting slide to the one that I typically do, saying, if you are interested in large language models and specifically the trust and safety aspects, how do I get these things to behave in ways that are acceptable to shareholders and users and governments and stakeholders of all kinds, then feel free to reach out to me, Aaron B. Goldman on LinkedIn. And with that, I will just say that The low rank adaptation of large language models is a paper that I love. All right. Are there any questions?
One question I had that I think you kind of answered though was I found interesting was that how is it that it's still able to maintain kind of the same quality even though it's a lot less smaller parameters that you're training or that you're updating? Um, and more so, how is it that because you're still running through the old model and this low rank kind of adapters, how is it that it doesn't introduce latency? Uh, because it mentions that other adapters do introduce latency. So that's kind of one thing I wasn't sure how is it that there's no latency here?
Yeah, so it depends how you're doing it operationally.
Hmm.
If the thing that you're doing when you're generating answers is run it through the conventional model and run it through the Laurel and then add the results, then you will add a tiny amount of latency because you have this addition step. You will also increase the amount of GPU memory you need because you've increased the size by the Laurel. And you have to accept those costs when you're doing training because you're keeping all of the fixed things fixed and you're only modifying the laurels. But once you're trained, well, I now have this matrix and I have a laurel that if you multiply it out is the exact same dimensions as the large language model was. So what you do is you load it into memory, and then you take the Laurel and you multiply it out to be the same dimensions, and then you just add all of the parameters in all of the places in the large matrix that is the equivalent of if you had gone through the two sides separately and put them together.
Mhm.
So it leads to this effect of, let me reshare this. So here we have this foundation model that's 500 gigabytes. And then we're adding 64 gigabytes of Laurel and 8 gigabytes of Laurel and 1 megabyte of Laurel. So what is the total combined size? It's still 512 gigabytes. Because each time I add one of these, I'm multiplying it out and adding it to the largest one, and multiplying it out and adding it to the largest one, and multiplying it out and adding it to the largest one. So the total in-memory time when I'm doing inference is the exact same dimensions of the matrix I had before. It's just all of the values have been tweaked slightly with values that happen to be aligned nicely with the bent principal component analysis I did when I did the decomposition. Changed a lot. And the ones that were not really on that high dimensionality. Um, with the real beauty being that those are potentially different. So the numbers that are most modified by my subject matter expert or my task expert or my user personalization may be different numbers in the multiplied out matrices because of the shape of the first matrix is essentially re-angling everything to the dimension that is best for learning my task. And then my scale is learning my task. And then the third matrix is shifting it all back to where it was. Well, when I multiply them all together, now where my changes end up are kind of spewed all over the matrix and will be largely independent as I learn largely independent tasks. So that gives me the ability to do them. Um, it also kind of accidentally, one of the problems that we've been working on for a long time in large language model systems was how do we do distributed training? Because it's hard to like add together the training of a bunch of different things. But now we've sort of stumbled across it of once you've spent the enormous amount of effort in one place to generate a foundation model, well, now if you train based on a foundation model and I train based on a foundation model, we can totally add our laurels to each other because they're highly likely to be independent but they're also highly likely to have their dimensions be so similar to each other that they both look like the foundation model and can be added to that. So now we get this nice game of great. You train a Laurel that's subject matter expert on the law. I'll train a Laurel that's subject matter expert on my business's super secret private intellectual property. And now I will ask questions of the model that has been told my super secret proprietary information and your public knowledge expert.
Cool. Thanks.
Um, so that's why you don't add latency. Your first question was why do you have enough space that you can actually learn things, I think?
Or what it was more about like I found it interesting that you don't lose or you kind of maintain model quality even though you're only updating a few parameters compared to the original model.
Yeah, so this mostly comes from other paper experiments that's not in this paper, but fundamentally you run into this thing that the truth tends to be much lower rank than the actual matrix. So if you try to do a singular value decomposition of one of these matrices that has been trained, what you find is that almost all of the energy is in the first few ranks, with first few being like 320 of the 2000. And then it starts dropping off, and the lower ones end up being noise. I think the best example there is the thing with like the faces. Where's this slide? When you take one of these models and you do the principal component analysis on any particular concept, what you tend to find is the ones that are near the front, if you look at them, they're incorporating large amounts of that actual conceptual information. And the ones that are near the bottom, when you decompose them in that way, are essentially Gaussian noise. And to some extent, that is a side effect of the model has to be much larger in order to learn the enormous number of concepts that you get by training on all of the text humanity has ever generated and a ridiculous number of images than the amount that is necessary to represent any particular subject or any particular task that you are trying to do. So,
Mhm.
in some sense, you only need to change a very small amount of the information in sort of the same ways that, like, imagine that I hired you to come work at my company and we're refrigerator salesmen and you know nothing about selling refrigerators. For me to teach you to be a good refrigerator salesman, I actually have to change a very small percentage of all of your beliefs. The fact that you believe if you throw an apple up in the air, it will come to a stop and fall back to the earth, you're going to believe that whether you are or are not a refrigerator salesman. So the trick with the Laurel is when you are teaching one of these systems a new task or a new subject matter expertise, you're actually changing a very tiny percentage of its beliefs. And when I stop to think about it that way, it's like, wait a second. The fact that these laurels are, a 10,000th of the size of the entire thing. Like, if you summarized everything you knew in 175 gigabytes of data, I think most things you would learn now would be less than 18 megabytes of data. Like, how often do you learn a new task that requires you to change even a 10,000th of the things you believe? I don't know if that makes sense as an analogy or.
Yeah, no, that makes sense. That was a good one. Thank you.
All right. With that, I will stop the recording. Thank you.